So now it's time for the presentation of multi-FEAT, multi-feature edge alignment for targetless camera LiDAR calibration. This paper is going to be presented by Professor Raj. Please go ahead.
Yeah, thank you again. Here I am back. Yeah, as a co-organizer, I made sure this presentation is short and it saves some time for us. So early this morning, I was talking about estimation, inference, control problems in the absence of infrastructure, right? So how do we solve problems when there is no reference? And this is one of those tiny challenges that we face, as my previous speakers also mentioned, Robert, I think, about calibration. And this is a specific calibration problem, which is the camera calibration problem. And how do we calibrate cameras? And how can we do this without a reference, right? So just to give an idea, this is one of our master students. His name is Yeri Rovers, surprisingly, right? So he is sitting in S-Tech and he's trying to calibrate our lunar zebra. Also gives you an image of how tiny our rover is. And what he's doing is trying to actually hold a checkerboard in front of the rover and trying to say, please calibrate my camera, right? And this is obviously a problem because we can't, sort of have checkerboards and QR codes for a swarm of rovers. So this is not a sustainable solution. So mathematically, how do we try to do this problem is, okay, essentially you want to estimate some rotation matrix and translation vector, and you have a coordinate system of the camera. And given the known checkerboard coordinates, you basically want to find an R and a T. And so rotation is just the rotation of the camera itself, and the translation is the phase shift, spatial phase shift, right? And the question we are trying to pose is, can we calibrate our cameras without a checkerboard or a QR code or an external reference, right? And how do we try to do this? We exploit another sensor which is on board. So you can obviously say, okay, I can use multiple cameras, but I can also use, let's say, a LiDAR, for instance, right? So that's the trick. The trick is essentially to use another sensor modality and try to relatively calibrate them, right? So because both these sensor modalities or other sensor modalities are on the same agent and the same rigid body structure, so rotation and translation parameters should be, estimatable. But obviously, when you have another sensor, you have other pre-processing challenges. In case of LiDAR, for instance, you have a 3D sensor, and then your camera is a 2D sensor. You get an image, and whereas LiDAR, you get your point clouds. And so this 3D to 2D projection mapping has its own loss problems and other issues. So what we came up with was an entire pipeline, starting with LiDAR, doing some occlusion detection, collecting a lot of features from LiDAR, and this multi-feature collection is what gives the prefix multi-FEAT, to our FEAT algorithm. And what we try to do is also do a lot of pre-processing for camera, and then try to compare these images. And when we look at these images, instead of using checkerboards, we're going to use reference objects in the frame as our checkerboard, and then use the contours of this reference object as a reference to sort of find our rotation and translation parameter, right? So if I look at a very popular automotive data set, which is the Kitty data set, you have typically an image like this, and these colorful lines that you see on top of it is just the LiDAR lines, right? So as you can see, they are completely not aligned, and that's because the camera is not calibrated at all. So if I calibrate my LiDAR and camera, then I have my expected output to be like this. And that's the goal we want to achieve in the absence of a checkerboard, right? So the details of the paper are there on arXiv for anyone to read. So I'm just going to expand on what I'm talking about. For image processing, we can do these segment extractions, and more recently we have the SAM algorithm, which Meta came up with. But there's a lot of semantic edge detection solutions out there. So we picked up one off the shelf, and then we use a lot of gradient-based kernels to find these edges and the contours. And obviously, with some Gaussian blurring, we have a very good collection of objects that are there. So in this case, you have a car, you have pedestrians, but what we're interested is just the contours of these objects, right? When it comes to point cloud processing, one of the key challenges that we face is there's a lot of holes in the point cloud data, right? The LiDAR data. And these holes occur especially in the contours. So if you see this bicyclist, you see on the edge, there is a lot of occlusion that happens. So we have to mitigate those occlusions. So we come up with local sort of smoothing filters around these occlusions, so that we have occlusion-free object detection from the point cloud processing. And as I said previously, we collect a lot of dense feature maps, and we try to collect these edges across in various different ways by training various different kernels. And in a sense, we try to collect depth, reflectivity, foreground objects, and ground plane, and we try to separate them out, and we assign certain probabilities to each one of them. And the combined result is then put through an optimization problem where we try to say, all right, here's my edge map from the camera, here's my edge map from the LiDAR, and how can I probabilistically combine them and try to fit them nicely, right? So there's some normalization parameters, but these can also be tweaked. And fortunately, the kind of problem that we are posing can be solved by, gradient descent-based methods. So this is, again, an off-the-shelf solver. And what happens then in the final output is that, we obviously get these images and the LiDAR points aligned. And we are not the first ones to come up with this idea. A lot of previous works which has been done by Castrina, by Pandey, etc. And so what we try to do is now plot all the rotation and translation parameters on the y-axis, and the x-axis, what we are trying to show is basically the error, right, of the residual, of the cost function, sorry. So when I look at cost functions of Pandey, Levinson, Castrina, you can see they are a lot more serrated. There are a lot of local minimas where your solver can get stuck at. So you may get a completely wrong rotational translation parameter. The success of our pipeline is we have a much more smoother cost function. That's number one. But most importantly, we are mostly centered around zero, right? So we are able to also mitigate the bias problem, which ensures that our solver always gives you the right rotation and translation parameter, right? In the absence of a checkerboard, right? That's the critical thing. And obviously, this is a very nice frame because all the objects are very clearly distinguishable, but we also tested it in very different frames where, there is a lot of traffic or there's shadow areas and so on and so forth. So those images are available on archive for everyone to go and see. And what we noticed was consistently our cost function was smooth. It didn't have a certain PDF, but nonetheless, it had one local minima we can always converge to, right? So the whole summary of the thing is we propose a camera-LiDAR joint calibration framework. It's a lot of pre-processing involved so as to get a smoother cost function, and we get a unique solution every time. We do not use a checkerboard or a QR code, and so we use additional sensors on board to sort of propose a reference-free calibration, if you may. And of course, there's a lot of extensions you could do. You could have additional features, more key point detections, and so on and so forth. As I said, segment anything is a new model that Meta AI just released, an upgraded version, so we can also use that as a plugin. And what I showed you was a single shot calibration, right? So I pick up a single frame of camera, a single frame of point cloud, and I calibrate it. But of course, you could collect as many snapshot images as possible, and you can sort of use Bayesian techniques to solve this problem. So in summary, essentially what we're trying to pitch is a reference-free camera calibration problem with the addition of another sensor on board. And that's the multi-feed pipeline for you guys. This is a work done by my master student, and also this presentation was made by him. So I want to thank him as well for this great work. Thank you again.
Thank you very much, Raj. Is there any question in the audience?
Yeah, thank you for this interesting presentation. I was wondering, do you need certain structures in your surroundings, like something that looks similar to a checkerboard or like a sharp edge of a house? Can you elaborate a little bit on that?
Yeah, so I think what we're looking for is edges. And in the context of this room, and the context of the kind of projects we're looking at in this room, let's imagine planetary exploration. And there, of course, in the absence of a certain rock, then you're in trouble. So then what we try to rely on is the horizon. If you have your ground plane and you have that horizon, that's good enough, right? And of course, that's very limited because that's just a line on the horizon. But at least it gives you rotation translation up to a couple of dimensions, not all 3D, but to some extent it can resolve it, right? And so that actually causes that optimization problem to be a bit ill-posed. right? So that's one of the challenges. Yeah, but you need to have some sort of object. Otherwise, the other trick is if you are considering a swarm, swarms can look at each other. That's another trick that we do, and that's obviously done in a lot of competitions where we put QR codes on our bots and ask each other to look at each other. But here you could also look at any other lander, any other bot which is non-cooperative. You have no clue, and you can just look at them and then calibrate your camera, which is the more interesting thing. It's almost non-invasive and passive way of calibrating. Right? That's what excites us more. Yeah.
Thanks for the interesting talk, and a very short question to save time for lunch. Did you have any experience with stereo calibration on this?
Sorry.
Or did you ever launch this method on stereo calibration?
No, not yet. So that's the extension that we are also looking at. So stereo calibration is also another thing because the Lunar Zebra will have stereo vision. So that's one of the things that we'll look into. Yeah.